And we're back. This is section 8.2, constant coefficient homogeneous linear differential equations. All right, so in this section, we're going to look at how to find complementary solutions to linear differential equations. Now, we will do that by substituting in y equals e to the rx into the differential equation and solving for r. Now, the resulting polynomial that is going to have one of three options. It's going to have distinct real roots, it's going to have repeated real roots, or it's going to have imaginary roots. Okay, so if it's distinct real roots, okay, where the roots are r1, r2, r3, then the complementary solution is going to consist of functions like e to the r1x, e to the r2x, and so on. If you have repeated roots, then the solution is going to look like e to the rx, x e to the rx, x squared e to the rx, and so on. And if you're going to have real roots, then the solution will consist of functions like e to the ax cosine bx and e to the ax sine bx. So let's take a look at the general form for the general type problem that looks at distinct real roots. So I'm going to give you the differential equation that we looked at last time, y double prime minus 2y prime minus 15y equals 0. Last time meaning the section 8.1 video. And we're going to find the complementary solution to it. So we substitute in y equals e to the rx. So you get r squared e to the rx when you take two derivatives of this. Substitute in for y prime. R e to the rx is y prime, so that's 2 r e to the rx, and y is e to the rx, so that's 15 e to the rx. Now, every term has an e to the rx that can be factored out, so you do that, and you're left with r squared minus 2r minus 15 times e to the rx is 0. Now, this will always be the case that it takes this form. So, you pick off the coefficient on y, and that's down here. Take the coefficient on y prime, and that's minus 2r. That's r to the first power, the first derivative of y. And this is the second derivative of y, so that's an r squared. This is called the auxiliary polynomial. And it results from subbing in y equals constant e to the rx into the linear homogeneous differential equation. So in solving this equation, you can see that r equals 5 and r equals negative 3 are solutions. Okay? Therefore, this second order differential equation has two linearly independent solutions to it, e to the 5x and e to the negative 3x, and scalar multiples of each. So the general solution to the differential equation is constant e to the 5x plus constant 2 e to the negative 3x. Okay. So that's the type of process that you would use when solving auxiliary polynomial with distinct real roots. What about repeated real roots? Okay, so that's right here. Distinct real roots and complex roots are a little bit more complicated, and they require a little bit more discussion. So let's give you an example of a differential equation that will result in an auxiliary polynomial with repeated real roots. So take y double prime plus 10y prime plus 25y equals 0. So your auxiliary polynomial is going to be r squared plus 10r plus 25 equals 0. You can jump straight to that. You don't have to make the substitution when solving these. So this factors down to r plus 5 and r plus 5. So you get r equals negative 5 is a root with multiplicity 2. Okay. Now we have to determine what the multiplicity of the root has, how the multiplicity of the root will impact a general solution to the differential equation. So let's take a look at the problem from the top. Y double prime plus 10y prime plus 25y equals 0. Now, remember, another way of writing this is going to be d squared y dx squared plus 10 dy dx plus 25y equals 0. Okay, and if we treat these, okay, kind of as fractions, you end up with something like this, which can be factored in a way that looks like that. Okay, so taking our initial differential equation, okay, we can write it in a manner like what's right here. Now, I'm going to go through some mathematics that you might find a little bit confusing. Okay, realize that you don't have to reproduce this every time we solve the problem. Okay, this is kind of a one-time thing, but it's going to give you an idea of the mechanics of what's going on here. We're going to define u of x to be d dx plus 5 times y. Okay, so that means in the equation above, d dx plus 5 times y, u, is equal to 0. Okay, now this right here I write has solution u of x equals c e to the negative 5x. Where is that coming from? Okay, that's coming from du dx plus 5u is equal to 0. Okay, that's like saying r plus 5 is equal to 0, because that's the auxiliary polynomial for this differential equation. So r equals negative 5, so that means the solution looks like constant e to the negative 5x. Okay, this is a linear auxiliary polynomial with one real root. So if u of x equals c e to the negative 5x, I can take this information and I can replace u of x with c e to the negative 5x in this definition. So c e to the negative 5x is equal to d dx plus 5 times y. Now, d dx plus 5 times y is the same as dy dx plus 5y. Distribute it. So, dy dx plus 5y is equal to c e to the negative 5x. This is a first order linear differential equation that has, where the coefficient on dy dx is 1. Okay, the coefficient on y is some function of x. It's a constant function of x, but it's constant. It's a function of x. And this right here is some function of x. That is of the form of the differential equations we solved using the integrating factor. So the integrating factor is e to the integral of what's in front of y here, so that's 5 dx, so that's e to the 5x. If I take this and I multiply everything through by e to the 5x, I get e to the 5x y prime plus 5e to the 5x equals c times e to the negative 5x times e to the 5x, so the 5x and the negative 5x cancel, and you're left with c there. The left-hand side doesn't factor. It can be written as a product of the derivative of a product, sorry. So it's the derivative of y and e to the 5x, okay? Integrating both sides, I get y e to the 5x is cx plus d. The integral of a constant is cx plus another constant, that's d. And dividing both sides by e to the 5x, I get this to be y equals cx e to the negative 5x plus d e to the negative 5x. So there's your general solution. Okay, there are it's a second order differential equation. You have two linearly independent solutions. What I mean is I can't multiply this by a scalar and get this over here. Okay, and the operative term is a scalar. So I can multiply this by x and get x e to the negative 5x, but x is not a scalar. I can't multiply it like by 2 or 3 or 5 or anything like that and get x e to the negative 5x. So when you have roots with multiplicity 2, you have two independent solutions, e to the rx and x e to the rx. If you have roots with multiplicity 3, you have something like e to the rx, x e to the rx, x squared e to the rx. If you had multiplicity 4, then you'd have this plus x cubed e to the rx, and so on. All right. What about complex roots? Okay, so if you have a root like r equals a plus or minus bi, how do we treat that? Well, that implies that e to the a plus bix and e to the a minus bix are independent solutions to the differential equation. So you have a real valued homogeneous linear differential equation with an complex solution to it. We don't want a complex solution. We want a real solution. Okay, so how can we get a real solution to it? Well, by Euler's formula, you can take e to the a plus bix and write it as e a to the x times cosine bx plus I sine bx. We looked at that way back in, section 7.12, somewhere around there? Yes, thereabouts. And y2 of x, okay, the equation e to the a minus bi of x is e to the ax times the cosine of bx minus I sine bx. Okay. Now here's where it gets interesting. Okay, you can take these two independent solutions to our real valued differential equation, and the solutions to our a homogeneous differential equation. Okay, the key word here is homogeneous differential equation, is a subspace. We've proven that before. Okay, so that means all linear combinations of y1 and y2 will also be solutions. Okay, because the solution set of a homogeneous differential equation is a subspace, then it's closed under addition and it's closed under scalar multiplication. So all linear combinations of y1 and y2 are also going to be solutions. Okay, our goal is to take these complex valued solutions and find real functions that are solutions and use them as replacements. So how do you do that? Consider these. Okay, you have 1/2 y1 plus y2. What's 1/2 y1 plus y2? So y1, write that in purple, is e to the ax cosine bx plus I sine bx. Y2 is e to the ax times cosine bx minus I sine bx. Okay, if I were to combine these, what would I get? Let's take a look. So 1/2 e to the ax cosine bx plus e to the ax I sine bx plus e to the ax cosine bx minus e to the ax I sine bx. Well, what do we have here? We have a positive I sine bx, and we have a negative I sine bx right there. Okay, those will zero out. So we have 1/2 times e to the ax cosine bx and e to the ax cosine bx. That's 2 e to the ax cosine bx's. These 2's cancel, and you're left with e to the ax cosine bx. So using the property of closure, we can say, since these are known to be solutions of the differential equation, linear combinations of those two functions will be a solution to the differential equation. And this one that you obtain by adding the two y1 and y2 and multiplying by 1/2 happens to be one where there's no imaginary numbers in it. And a real valued solution to a real valued differential equation is preferred. Okay, so there you go. As far as the another solution, okay, let's subtract y1 and y2, and then divide by a scalar, and that scalar is going to be 1/2i. All right, so take this, go 1/2i, y1 minus y2. What does that give us? It gives us 1/2i times, big parentheses, fit all of it in there, e to the ax times cosine bx plus I sine bx. That's y1, and this will be a minus sign, e to the ax cosine bx minus I sine bx. And we'll take the difference. Okay. 1/2i times, simplifying the inside, e to the ax cosine bx plus e to the ax I sine bx minus e to the ax cosine bx minus the negatives, that's plus, e to the ax I sine bx. All right, so there's going to be cancellation. Where is it? Right here and right here. So what you're left with is 1/2i times e to the ax I sine bx and e to the ax I sine bx, so that's 2i e to the ax sine bx, and this 2i cancels with that 2i, and you get e to the ax sine bx. All right, and this solution right here is a real valued solution to the differential equation, as is this, and neither one of those two circled are scalar multiples of one another. Okay, so we can instead use these two as representing a solution to the differential equation. In other words, okay, if this was a second order differential equation, the basis of, there would be two linearly independent solutions to the differential equation. We could use y1 and y2 because they're linearly independent solutions. y1 and y2, they're linearly independent solutions to that second order differential equation. Or we could use these two. because they're linearly independent solutions to the differential equation. Because these are real valued functions and these are complex valued functions, we prefer to use the real ones. Okay? And henceforth and forevermore, we can always take our solution and jump to e to the ax cosine bx and e to the ax sine bx whenever we're getting complex valued roots to our auxiliary polynomial. Okay, so there we go. Consequently, e to the ax cosine bx and e to the ax sine bx are real valued functions that solve the differential equation. Okay, at this moment, I'm going to take a break. Make sure the video is not too long before we jump into solving the problems that you see on your screen.